All right, it's started. It's about the time. Let's start our class, okay? Any questions do you want to ask before I started? Just now we talked about the last class. Any questions? Any questions? Okay. If you don't have any questions, then let me show you again about the grados. Okay, I'll show again using grados. All right, so I already have this data in grados. All right, so I'm using LNEX. I showed from the beginning that I wanted to see the plot. Okay, so you can just hit this one and you may see the view. Okay, then I'll see the time series plot. Okay, and this is the time and this one. Okay, and I hit OK. So this is really what I see from eViews too. Okay, then all right, then I can also see the correlogram. Okay, here I have the function of correlogram. And how many legs? So I'm using 36. Okay, then I hit OK. I think this is a correlogram which we just see from the eViews. Okay, I think I don't have that in eViews again, but this one is the grados. Okay, again, we're looking at these numbers. This is so-called autocorrelation function, and the numbers is from 0.9985 up to 0.9399, about 94 up to the 36 lags. Okay, and they are all very significant. Means what? Means they're non-stationary. Okay, and I think the rest of them, you know, maybe you can, this p-value is according to the ACF. Okay, or also Q statistic, but never mind, you can just look at the numbers and looking at the correlations, since this is pretty close to 1, so it's highly correlated. Okay, so they're non-stationary. Okay, then okay, I'm looking at the unit root test. Okay, unit root test. Oh, here I do have correlogram too. Okay, so you can check it from here. Okay, unit root test. And this is augmented Dickey-Fuller test. First of all, lag order for ADF test. So I'm using 12. Okay, the criterion is archaic information criterion. There's only 2. This is SWOS. Okay, this is archive. Okay, now I have to choose these 3 versions, which one. So I'm taking with constant and trend. So I click here with constant and trend. All right, and then I use level of variables. Okay, so these three parts It's just as what I did using the eViews. Okay, then I hit OK. Okay, here is the output. So let's see the output. Augmented Dickey-Fuller test for LNEX. Testing down from 12 lakhs. Then criterion is archaic information criterion. Then our sample, since this is using the lag, so I have 2,355. Then I have one lag, so is 25. A unit root test is here. A is what we call the beta 1 equal to 1. Okay, and look at the result. Look at the model here, and the estimated value of the beta is 0.0. Let me show this Gradle's output. Okay, look at the coefficient here, negative 0.004088. And this is exactly the same thing. Okay, then test statistic is negative 3.26 something, exactly the same as eViews. Then the p-value 0.1248 is pretty close here. Okay, so according to this result, we know that we cannot reject the null hypothesis. Therefore, we are not able to show this variable is stationary. So any questions so far? You can go back home and play with that. If I extend, so for example, if I do this unit root test, if I add those maximum up to, even higher, since this is daily data, okay? Then is there any change? So look at the eViews. There's no change. Look at these probabilities. Even, still not reject the null hypothesis. Okay, so same thing here. If I'm working with this is 24. This is, I do have the same. I do have the same result. Okay. Any questions so far? And since we really
Professor,
wanted to, yes.
I want to ask about the result of augmented Dickey-Fuller statistic. They have if the result of the statistic, they have the three of the level of critical value 1, 5, 10. Which one we have to choose for critical value?
You mean the critical value?
Yes.
Always look at the upper parts of here. This is the this is the, actually this is called augmented Dickey-Fuller tau test.
Yes, bro.
And since this augmented Dickey-Fuller tau test, they are not using the t-table's critical value.
Yes.
So this is according to the tau test critical value, which is really different from
T-table.
the t-tables.
Yes.
So do not look at the probability here.
Yes.
You have to look at the probability here.
Yeah.
Although this statistics is the same. Okay, this is based on the different critical values, the tau test instead of t-test. So the probability is different from the t-tables. So look at the upper parts here. Look at the upper parts. Do not look at the lower parts, the second parts here.
Yeah.
Look at the upper parts here. Is that clear?
Yeah, clear, bro. It means we can choose any one negative field 1, 5, or 10%, right?
Either one of the, either one of them. But usually we don't really restrict it to the 1%. You can, use up to 10%. And here, for our example, even 10%, this probability is larger than the 10%.
Okay.
Do not stick just only on 1% or 5% only.
Yeah. Okay, bro.
Okay, just look at the probabilities.
Probability, yes.
If it is greater than 10%, then you're not able to reject the null hypothesis.
Yeah. Okay, bro. Thank you, bro.
Okay.
Okay, bro. Thank you.
Yeah, Professor, I have another question.
Yes.
You said before that if we test the lag level, it can be used as 1/3 or 1/4 of the data. So why we would use 24?
Oh, okay. 1/3 or 1/4 lag is using parallelogram instead of here. I just mentioned that the lag, okay? If you're using parallelogram, this is what we say the parallelogram. Parallelogram. If you use it using this one, the lag here, we can use up to what? 1/3 or 1/4 of the original data. So for example, we have 2,355. I can use 1/4. And what are they? It's about 600, right? So let's make it 600. Make it 600. Okay. Then look at the parallelogram. Let's look at parallelogram. The AC. Look at this one. Even this is really, really high. Up to the last one, the correlation is still 0.726. It's still high.
So how much we will conclude is a small number, or like?
This is correlation, right? So correlation is between +1 and -1. So if your numbers is pretty close to +1 or -1, we'll say they're really is highly correlated. If they're pretty close to 0, means there's no correlation, because I wanted to see there's no correlations. But here we see all this observation. This is the daily data. So for daily, the correlation for daily data is highly correlated. So means they're really, really correlated. Okay, if they're really correlated, there's a possibility that there's a zero correlations. And one of the reason for spurious regression is the zero correlations. And all the zero correlations may created to the non-stationary of the variables. So this is about the lack of parallelogram. And the one I just showed the unit root test, the lag here. Okay, if we have the annual data, okay, we may include just one or two lags. I mean, here it's one or two lags for annual data. For quarterly data, is 4 lags. You know, because 1 year is 4 quarters. Okay, so quarterly data, we're using 4 lags. And for monthly data, since for a year is 12 months, so usually we include 12 lags. Okay, and since this is the daily data, we can use more than that. So I'm just trying 24 again. And I try using 12 first, then 24. And this one, sometimes this is a try and error. Okay, so I try 12 first. And the probability and the Digifuller test is not reject null hypothesis. Now I tried 24th again, it's still not reject the null hypothesis. So now why don't I try 36? The result exactly the same thing. It doesn't change it. Means the more lags you increase, the probability won't change anymore. Okay, so you may try. You can play with that a while. And I'm just saying that for annual data, usually we use 1 or 2. Okay, so this is a general rule. Okay, for quarterly data, you're using 4. Then monthly data, using 12. Then daily data, you can use more lags too. But just try it. Okay, any questions?
No problem.
And when we talk about this one, we really like our variables is stationary, right? As long as we check our variables is non-stationary. Is there any other ways that make these variables stationary? Okay, I'll introduce 2 ways. First one, a common practice is to make a trending time variable stationary, is to remove the trend from it. Then we just see that our LNEX variables has a trend, right? So we may try to remove the trend from it. Then how do we remove from trend? Okay, let me show you. Okay, I'll do this EViews. Okay, and where's my original? Oh, this is my original data. Okay, if I want to remove the trend, okay, I can use the regret. I can estimate the regression using ln Oh, I'm sorry. What is this? Oh, this is not another data. This is not what I wanted. Okay, where is my data? Where's my original data? Oh, here. Oh no, this is all Gretel's. Where's my original data? This one? Where can I go back to my original data? Okay, here. No. Oh. Sorry. I'll go back to get mine. Okay, this is this one. Okay. All right. The first way is to remove the trend. How do we do that? Okay, I'll do this one with the trend. The time here is the t. Okay. So I'll do the regression. Okay, since I want to remove the trend. Okay. So I will do the regression of this one. And so after I do this one, then I'll get the residuals. Okay. So let me say I'm using residuals. Okay. So this is what I have done. After I run this one, okay, then I can generate the residuals using this one and is this one, okay? This is equal to the residuals. This residuals is the latest regression I run it, okay? So I'm using U equal to this residuals, and which I have already done it, okay? But whatever, I just done it again. Okay? All right. And this is U, this variable U is already removed the trend. Okay? Then I'm using the new variable, which is U. Okay? And I can see the I can see the trend. I can see the diagram of the U still. Look at this one. It seems that I still have trend. Okay, then I can look at the parallelogram again. Okay, up to 36. So this one. And look at this autocorrelations, autocorrelations. Okay, look at this one. Still is very high. All right. Then it seems that it's not okay. Okay. After I remove the trend, I also can use the unit test. All right. So I'm using this one. And what should I choose here? Since I still have trend, so I can use trend and intercept too. Let me see. Okay. And look at that. Look at my U test. It seems that after I take the times, the trend up, it is still non-stationary. Okay. So I know that after I take the trend out, I remove the trend, it still doesn't work. And the second way, so instead of detrending a time series, then that's suppose we take the first difference of the LNEX. Okay, so let me take the first difference of the LNEX. So the D1 here is what I did. What do I do? What do I do for the first difference in eViews? I can use I can use this one, generate. So I'm using D1 equal to difference of the LNEX. Okay, this is the D, just D, not D1, okay? I use the difference of the LNEX and make it another variable called D1. All right? Yeah, I hit OK. And this is what I have, D1 here. Okay? Then I can using the original three ways to see how this D1 look like. The first one is graphical. Okay, I view it using the graph. How does this look like? We did not see any trend, right?
Yes.
This is the first difference. We did not see any trend at all. Okay, all right. And if we look at, so let's see. Oh, I have to. Okay, if I using parallelogram, okay, I'm also using 36. Then hit OK. Look at this one. Look at this one. Autocorrelation numbers. Did you see that? Look at all this autocorrelation numbers. Isn't this number is pretty close to 0? 0 means no autocorrelation, right? Okay. Then, if I use the unirule test, okay, well, this is the first difference. Okay. Well, what maybe I can try, since this is first the difference, maybe I can try no lags first. I'll try it, okay? All right. So what did you see? Look at these parts.
Excuse me, Professor. Can we
Yes.
choose the third first differences before? I think the previous choose the first differences.
No. For this one, the definition of D1 is the first difference, right?
Right.
Okay. Then, if I want to do the unit root test, I'm still using levels. Means that this one, this is not first difference.
Okay.
The definition of this one is really the first difference, but according to these variables, this is also the levels. If I choose the first difference, means the difference of this first D1, which is not I wanted.
Okay.
Do you understand what I'm saying here?
Yes, I understand. Thank you.
Okay. So according to the result, I'm just showing according to this T statistics, okay, this is negative 48 something. So 48 something. According to the tau test, the critical value is here. So the probability is 0. So means reject the null hypothesis. Therefore, the first difference of the LNAX is stationary. So that this is what I'm saying, that usually when we run in the regressions, first of all, we need to make sure all the variables, including y variables and x variables, are stationary. So how do we check whether they are stationary variable or not? Usually we're using 3 ways. Okay, and in our book, it's really focused on the unit root test, which means Dickey-Fuller test. Okay, but usually we're looking at 3 ways. The first one is just look at the graphical pictures of the original data, original variable. The second one is look at the correlograms of that variables to see the correlation of all the observations of that variables. The third one is look at the unit root test, Dickey-Fuller test. And for Dickey-Fuller test, we like to see the probability is reject the null hypothesis. Then it will turn, then will show that the time series variables is stationary. But sometimes when I make, just like our examples, we're not able to get a result of stationary series. Therefore, we need to find some other ways to make it stationary. Okay, then I show 2 ways. First is remove the trend, since there's a trend according to the graphical the pictures. Okay, their trend. So we can remove the trend. And we just did it, and it cannot work. Okay, then the second one, we're using the first, the difference of the original variables. And we did that, and it shows us that it become stationary. So in other words, if in this case, okay, instead of using original LNEX, you need to do the first the difference of LNEX as a variables. Because we just show that the first the difference of LNEX is stationary variable. Okay, but we will come up to the conclusions. When is better to use original, and when is okay to do the difference. Okay, there are some guidelines we can follow. Okay, and the author also give us some suggestion too, which is on our textbook page 403. 403. There's some guidelines, but we'll get to that because there's also another ways. Okay, I haven't finished yet. Okay, before what time do we have? Okay, still well, we have 15 minutes. Okay, and before we're doing that, let me also explain another data which really is the example of regression. This example is just one variables. Okay, just using and since we know that Dickey-Fuller test is based on the variables only. Okay, either y variables or x variables, either one of them is okay. Okay, so let me show you another data. Okay, and okay, so far, any questions? Any other questions you'd like to ask?
No, thank you.
No problem.
Okay, all right, let me show you another examples, okay? I'll get rid of that, delete, yes, save, no. Okay, all right. I'm using another one, which is the second data I give it to you, the PCE and PDI. Okay. And let me explain this data first. Okay. And this data set give us the quarterly data. So this is quarterly data on personal consumption expenditures, PCE, and personal disposal income, PDI. For the USA, for the from 1970 to 2008. So it's for total 156 observations. And this old data are in billions of $2,000. And again, I also take the natural log of the PCE and also PCI. So I take the natural log of PCE, it becomes a ln PCE and ln PDI for natural log of PDI. Okay. And now here comes the interesting question is the regression of consumption expenditures on disposable income spurious? So let's first look at a plot of the data. Okay. And how do we plot this one? Okay, I'll show these two variables. Open as a group, then I'll graph. Then I'm going to see this one. Okay, look at this diagram. What did you see from this diagram?
F20.
It seems that both LMPCE and LMPDI are trending series. Okay, if we look at the, this one, it suggests that these series are not stationary. And look at this one. The gap between these two. Well, yeah, the gap between these two is pretty similar. Okay, and if we and we can try later whether, remember we just have this ln-ex. After we take the first difference of the ln-ex, it becomes stationary. So we may have the same story as our ln-pce or ln-pdi. We don't know, okay, but we can check it later on. Okay, and let's see, by individual variables, we can use the, okay, the Gefuller test to start. Okay, so using this delete. Okay, I'm checking with one by one. Okay, so I'll start it from ln-pce first. Okay, then I'm using the Gefuller test. Okay, since this is a trend, so I'm this parts. Okay, and this parts. Okay, and I didn't. I just say that this is a quarterly data, right? Yes, this is quarterly data. Okay, am I right? Yeah, this is quarterly data we have from 1970s to 2008. So which is about 38 years with 4 quarters. Okay, it's about 156. Okay, so since this is a quarterly data, so maybe I'll show the using maximum of 4. Okay, and since this is a trend variables, so I'm using trend and intercept. Okay, let's see. What do you have? What do you have? What's the? Let me see. How come this is 3 and this is 4? What happened? What happened, Elias? I didn't see that before. If I use this 4, this one leg must be 4 instead of 3. How come this is 3? Let me try it from 1, 2, 3, 4. Okay, it's a little bit weird. Let me try it. If I started with 1, since this is quarterly data, I can try up to 4. Okay, now, so I try from 1 up to 4 to see what happened. Look at this one. You all see that? if I use 1, this one should be 1. So if I use lag is 1, this is non-stationary, right? So if I tried it 2, okay? If I use 2, this one should be 2. And this is non-stationary again. And if I use 3, this is a 3, okay? The probability is stationary. Then if I try 4, I just did it 4, right? But again, this is the result as the same as 3, since it is 3, okay? So we know that if I put 1 or 2, okay, then it become it's non-stationary. But I put it like 3 and 4, it's become stationary. Maybe I'll trade maybe higher. How about 5? You know, sometimes you need to try and error. Okay, if I use 5, the result is same as the 3. So in other words, if I use longer lag, the result will be the same. Okay, so if I try 8, okay, actually the result is the same as 3. So if I try 1 or 2, it's non-stationary. After 3, starting from 3, it's become stationary at 5% level. Okay? All right. How about PDI? How about LMPDI? Okay, I will do it. It is the same. Okay, then I'm level and trend. Okay, then I started from 1. It shows that if it is 1, this is non-stationary. Okay, if it is 2, okay, the same result as 1 is non-stationary. About 3? Well, up to the lag of 3 is stationary at 10% level. All right? Oh, 4. Okay. Okay, 4 is the same as 3. Let me see. Maybe higher, 5. You will see the lag is longer than the same as the result as number 3. Okay, so these two variables, LMPCE and LMPDI, are stationary when the lag is starting from 3. Okay? All right. I think it's run out of time today, and I'm going to start with this example of LMPDI and PDE next week. Okay? Any questions so far
Okay.
for today's? Okay, I like all of you really, review what we taught today, and also look at the books. Okay, read the books. And next week, not only for those Dickey-Fuller tests, I'm going to also introduce the co-integration, okay, which is also included in the section of 12.5. Okay, read it carefully. Then we'll do some more examples. Okay, then we'll know much better about the spurious regression and all this Dickey-Fuller test and co-integration next week. Okay.
Okay, thank you. Professor, just one small and quick question.
Okay.
Does that we would look at the probability is stationary, right? But you said that it is the 10% level. I think it is also this applied to the 5% level and 1% level. Is that correct?
Well, if it is 10% level significant, it doesn't really mean 5%. It will pass 5%, neither 1%. If you pass 1%, for sure, 5% and 10% passed. So if it is just 10%, it really doesn't imply 5% passed.
But in this case, it seems also passed.
One is 5% passed. The other one is 10% passed.
Okay, thank you.
Okay, all right. So we'll come back to this example next week. Okay, you can also go. You can also go back home and play with that by yourself, and you will see how to work with EViews by using Dickey-Fuller test. Okay.
Okay.
Okay,
All right.
thank you.
All right. Then let me stop the recording.